The universe is an endless expanse of mysteries, stretching beyond the limits of our imagination, filled with wonders so strange, they challenge everything we think we know. Out there, hidden in the vast darkness between stars, lie cosmic structures so bizarre, so utterly perplexing, that even the brightest minds can only stare in awe and wonder. Picture this: colossal rings of galaxies spinning in perfect unison, vast cosmic voids where nothing should exist, and ghostly filaments of matter weaving through space like threads in an invisible tapestry. These aren't just anomalies, they're cosmic puzzles begging to be solved, and today we're diving deep into 25 of the most mind-bending galactic structures ever discovered. What if I told you there's a place in the universe where galaxies align in a way that defies all logic, or that some regions of space are so eerily empty they seem to mock our understanding of physics? These aren't science fiction, they're real, they're out there, and they're waiting for us to uncover their secrets. Each one tells a story of forces we don't yet understand, of cosmic blueprints written in a language we're still learning to read. And the more we discover, the more we realize how much we don't know. That's the thrill of it all. The universe isn't just stranger than we imagine, it's stranger than we can imagine. So let's set out on this journey together, venturing into the great unknown. We'll explore gargantuan walls of galaxies stretching billions of light years, mysterious radio circles that glow like cosmic halos, and clusters so dense they warp the very fabric of space-time. Some of these structures might hold clues to the origins of the universe itself, while others could rewrite the rules of physics as we know them. But one thing's for certain: by the time we're done, you'll never look up at the night sky the same way again. The cosmos is calling, and the adventure begins now. The Hercules-Corona Borealis Great Wall isn't just massive, it redefines our very understanding of massive. Picture a structure so vast it dwarfs the observable universe's other giants, stretching an incomprehensible 10 billion light-years from end to end. To put that into perspective, our entire Milky Way galaxy would appear as nothing more than a speck lost in its cosmic sprawl. This isn't just a cluster of galaxies, it's a filament, a twisting, interconnected web of galaxies, gas, and dark matter, so enormous it challenges one of astronomy's core beliefs, the cosmological principle. This principle states that, on large enough scales, the universe should look roughly the same no matter where you're observing it from. But the Hercules-Corona Borealis Great Wall throws a wrench into that idea. How can the universe be uniform when structures like this exist? Imagine stirring a cup of coffee and finding, instead of a smooth blend, a single unbroken thread winding through it, defying all expectations. That's the kind of puzzle astronomers are facing. Even more baffling is how something this colossal could form in the first place. The universe simply hasn't had enough time, based on our current models, for gravity to pull matter into such an enormous structure. It's like building a skyscraper overnight with only a handful of workers. It shouldn't be possible. Some scientists speculate that unknown forces, perhaps echoes from the early universe's inflationary period, might have seeded this titanic formation. Others wonder if we're seeing a flaw in our understanding of dark matter's role in shaping the cosmos. What makes this great wall even stranger is its eerie uniformity. Unlike chaotic galaxy clusters, it appears as a smooth, elongated ribbon across the sky, as if some unseen hand carefully arranged it. Could there be clues hidden in its structure about the universe's birth? Or is it a cosmic illusion, a trick of perspective that makes unrelated galaxies appear connected? The answers remain just out of reach, but one thing is certain: the Hercules-Corona Borealis Great Wall isn't just a structure. It's a challenge, a silent, looming question mark written across the heavens. But if the Hercules-Corona Borealis Great Wall seemed impossibly large, wait until you hear about the giant arc, a structure so vast and unexpected that it makes astronomers question whether we've been reading the universe's blueprint all wrong. Discovered in 2021, this mind-bending formation isn't a wall or a cluster but a graceful, crescent-shaped curve of galaxies stretching an astonishing 3.3 billion light-years across the night sky. To grasp its scale, imagine a bow stretched so wide it could cradle dozens of Milky Ways end to end. And yet, it's not the size alone that has scientists reeling. It's the fact that, according to everything we know about cosmic evolution, this shouldn't exist at all. The giant arc's sheer symmetry is what makes it so unsettling. Unlike chaotic galaxy clusters or tangled filaments, this structure traces a near-perfect arc, as if the universe itself drew a smile across the cosmos. But here's the problem. Our current models of large-scale structure formation suggest that matter should be distributed far more randomly across such enormous distances. Gravity simply shouldn't have had enough time since the Big Bang to sculpt something so coherent, so organized on this scale. It's like tossing a handful of sand into the wind and watching it fall into the shape of a cathedral. Nature doesn't work that way. Or does it? When researchers first spotted the giant arc, the immediate question wasn't just how, but if. Could this be a fluke, a trick of perspective where unrelated galaxies just happen to line up in a way that mimics a structure? Statisticians rushed to calculate the odds, and the numbers came back startling. There's less than a 0.0003% chance this alignment is random. That's like flipping a coin and getting heads 50 times in a row. Possible, but so unlikely it forces you to question the coin itself. Skeptics argue we might be seeing a survivorship bias, where we only notice the rare patterns in the cosmic noise. But supporters counter that the arc's galaxies share similar ages and compositions, hinting at a deeper connection. The debate cuts to the heart of cosmology itself. If structures like the giant arc are real, they could upend the standard model of how the universe organizes matter. Some theorists suggest primordial gravitational waves, ripples from the universe's explosive birth, might have imprinted these patterns like fingerprints in wet clay. Others speculate that dark energy, the mysterious force accelerating the universe's expansion, could be shaping matter in ways we don't yet understand. But perhaps the most thrilling possibility is that the giant arc is a signpost pointing to physics beyond Einstein's theories. A cosmic clue that gravity itself works differently on scales we're only beginning to map. For now, the giant arc remains a celestial enigma, a question mark written in starlight. Every new telescope, every deeper sky survey brings us closer to understanding whether it's a statistical mirage or a revolution in the making. One thing's certain, the universe keeps finding ways to surprise us, and the giant arc is its latest, most elegant challenge yet. Some cosmic oddities look like they were designed by an artist rather than born from chaos, and Hoag's object might be the universe's most stunning masterpiece. Floating 300 million light-years away in the constellation Serpens, this peculiar galaxy appears as a near-perfect ring of young blue stars encircling a golden, spherical core, a structure so symmetrical it looks like a celestial bullseye painted across the void. Most galaxies clump into spirals or blobs, but Hoag's object defies categorization, leaving astronomers torn between two explosive explanations. Was it forged in a cataclysmic collision or sculpted by unseen waves rippling through cosmic gas? The collision theory paints a violent origin story. Imagine two galaxies, one perhaps a spiral like our Milky Way, smashing into each other billions of years ago. The impact could have scattered stars outward like debris from a shattered pane of glass, while the dense central bulge survived intact. Over eons, gravity might have shepherded those scattered stars into the ring we see today, a frozen snapshot of celestial wreckage. Supporting this idea are faint, wispy trails of stars around Hoag's object, ghostly fingerprints that hint at a long-ago encounter. But there's a problem: the ring is almost too perfect. Collisions tend to leave messy, lopsided remnants, not pristine circles. This flaw in the theory has given rise to an alternative where resonance, not destruction, shapes the galaxy. Picture dropping a pebble into a pond. The ripples spread outward in perfect rings. Some scientists propose that gravitational waves or density fluctuations in Hoag's primordial gas could have triggered similar ripples, compressing gas clouds into a star-forming wave that ignited the brilliant blue ring. If true, the galaxy didn't form from chaos but from rhythm, a cosmic vibration frozen in starlight. Adding to the mystery is the ring's eerie isolation. Unlike most ring galaxies which sit near potential collision partners, Hoag's object floats alone with no obvious culprit for a crash. Even stranger, telescopic deep-field images reveal another perfect ring galaxy lurking far behind it. A statistical fluke so rare it feels like the universe is teasing us with echoes. Whether accident or artistry, Hoag's object challenges our assumptions about how galaxies evolve. Perhaps the most mesmerizing detail isn't in the science but the sheer beauty of the thing. In a universe of sprawled spirals and formless ellipticals, Hoag's object stands apart, a cosmic mandala that seems almost meditative. It reminds us that the cosmos isn't just a place of forces and equations, but of patterns so exquisite they take our breath away. And somewhere in that balance between violence and harmony, chance and design, lies the secret of this celestial wonder. Most of the universe looks like a bustling metropolis, galaxies huddled together in clusters, strung along luminous filaments of gas and dark matter. But the Boots void is different. Imagine stepping out of a crowded city and into a desert so vast you could walk for days without seeing another soul. This is the Boots void, a staggering sphere of nothingness spanning 330 million light-years, where only 60 lonely galaxies drift in an ocean of darkness. To grasp just how empty this region is, consider this a typical patch of space that size should contain thousands of galaxies. Instead, the Boots void is a cosmic ghost town, a void so immense it could swallow our entire local group of galaxies without even noticing. The Milky Way would be like a single lantern flickering in an endless cavern. How does such a colossal void exist, and what does its eerie emptiness tell us about the universe's hidden blueprints? One leading theory points to quantum fluctuations in the early universe, tiny ripples in the fabric of reality that, when stretched by cosmic inflation, became vast empty bubbles in space. Picture blowing up a balloon with uneven thickness. Thin spots stretch into gaping voids, while denser regions knot into galaxy clusters. The Boots void might be one of those stretched thin patches, a fossilized imprint of the universe's quantum origins. But there's a twist. Some researchers argue the void isn't quite as empty as it seems. Those 60 galaxies aren't randomly scattered. They huddle in a rough line like pearls on a string. This unexpected pattern has sparked wilder speculation. Could this be evidence of a Type 3 civilization, one so advanced it has harnessed entire galaxies as energy sources? While captivating, most scientists dismiss this as pure science fiction, but the very fact that such ideas surface shows how deeply the Boots void unsettles our understanding. What truly fascinates astronomers isn't just the void itself, but its defiance of the cosmic web's usual rules. The universe should be homogeneous at such scales, yet here we find a gaping hole where matter seems to have simply vanished. Some suggest dark energy may have played a role, accelerating the expansion of this region faster than gravity could pull matter together. Others wonder if multiple smaller voids merged over eons, creating this titanic absence. The Boots void doesn't just challenge theories, it forces us to confront how much we still don't know about the universe's skeleton. Is it a fluke, or are there others even larger lurking in the darkness? Every answer we find only leads to deeper questions, and that's what makes this cosmic desert one of the most haunting enigmas in the sky. The Sloan Great Wall doesn't just stretch across the cosmos, it redefines what we thought possible for the universe's architecture. Discovered in 2003, this staggering filament of galaxies spans 1.4 billion light-years, a distance so immense it could bridge over 15,000 Milky Ways placed end to end. For years, it held the title as the largest known structure in the observable universe, a crown it wore until the Hercules-Corona Borealis Great Wall dethroned it. But size isn't the only reason the Sloan Great Wall remains a cornerstone of cosmic research. Its very existence pushes the boundaries of physics, forcing us to ask, how did gravity sculpt something this colossal in the time since the Big Bang? Picture the universe's matter as a simmering stew, with gravity slowly pulling ingredients together into clumps. According to our models, there's a speed limit to this process, a point where even 14 billion years shouldn't be enough time for structures as vast as the Sloan Great Wall to fully form. Yet here it is, a sprawling highway of galaxies, gas, and dark matter that defies those calculations. Some theorists argue that tiny quantum fluctuations in the early universe, magnified by inflation, gave this wall a head start. Others suggest we might need to rethink how dark matter interacts on these scales, or whether unknown forces gave gravity an unexpected assist. What makes the Sloan Great Wall particularly fascinating isn't just its size, but its intricate structure. Unlike a simple chain of galaxies, it's a complex web of intersecting filaments, knots, and voids, a microcosm of the cosmic web itself. This complexity offers a unique laboratory for studying how smaller structures merge and evolve over time. By mapping the motion of galaxies within the wall, astronomers have found evidence of streaming flows, where entire clusters drift along invisible rivers of dark matter, pulled by gravity's unseen hand. These flows hint at the hidden scaffolding that shapes the universe's largest patterns. Yet for all its grandeur, the Sloan Great Wall also underscores a humbling truth. Our view of the cosmos is still frustratingly limited. Because it lies relatively close, just a billion light-years away, its full scale is easier to map than more distant giants. But even here, perspective plays tricks. Some sections might be false connections, galaxies only appearing aligned from our vantage point. Untangling these illusions requires painstaking measurements of redshift and velocity, a reminder that the universe's grandest blueprints are still only partially decoded. As new telescopes peer deeper into space, the Sloan Great Wall stands as both a milestone and a mystery. It's a reminder that the cosmos builds on scales beyond human intuition, and that every answer we uncover reveals new questions waiting in the dark. Whether it's truly the universe's largest structure or merely the largest we've found so far, one thing is certain: the Sloan Great Wall isn't just a feature of the cosmos. It's a challenge written in starlight to keep looking further. If the cosmic structures we've explored so far have stretched your imagination, wait until you hear about the dark flow, a phenomenon so bizarre it suggests something enormous is pulling on our universe from outside. Picture this: hundreds of galaxy clusters, each containing thousands of galaxies, all drifting in the same direction at staggering speeds of nearly 2 million miles per hour. It's as if an invisible river is carving a path through the cosmos, tugging everything along with it. But here's the catch: there's nothing in the observable universe massive enough to create this motion. So what's pulling them? The answer might lie beyond the edge of everything we can see. This cosmic mystery first came to light when astronomers studied the cosmic microwave background, the faint afterglow of the Big Bang. Tiny temperature fluctuations in this ancient light revealed something unexpected: a puzzling dipole anisotropy, a fancy term meaning the entire observable universe seems to be moving in a particular direction. At first, scientists shrugged it off as a local effect, maybe our galaxy's motion through space. But when they mapped the movement of galaxy clusters using X-ray telescopes, the truth became impossible to ignore. These clusters weren't just moving randomly, they were being swept along in a coherent stream, like leaves caught in a cosmic current, and the source of that current Nowhere to be found in our visible universe, the implications are staggering. If the dark flow is real, it suggests the gravitational pull of something outside our cosmic horizon, a structure so massive it defies comprehension. Imagine standing in a dark room, feeling a breeze but seeing no open windows. That's the eerie situation cosmologists are facing. Some theorize it could be a supercluster of universes in the multiverse, a neighboring bubble universe so dense its gravity leaks into ours. Others propose it might be a remnant of pre-Big Bang physics, a relic from whatever existed before spacetime as we know it began, the most radical interpretation. That we're seeing the fingerprints of a higher dimensional structure bending our universe like a sheet of paper. Of course, not everyone's convinced. Skeptics argue the dark flow could be an artifact of incomplete data or systematic errors in measurements. After all, mapping the motion of galaxy clusters across billions of light years isn't exactly straightforward. But every time researchers refine their methods, the signal persists quiet, consistent, and utterly unexplained. Even more intriguing are recent studies suggesting the flow extends farther than initially thought, potentially spanning the entire observable universe. If true, this isn't just a curiosity, it's a fundamental challenge to our understanding of reality's boundaries. What makes the dark flow uniquely thrilling isn't just the science, but the philosophical door it cracks open. For centuries, we've assumed the universe is all there is. Now, we're staring at evidence that something, perhaps an entire other cosmos, might be out there tugging at the edges of our reality. It's a humbling reminder that the universe's greatest mysteries might not be in front of us, but just beyond the limits of our sight. And until we develop telescopes capable of peering past the cosmic horizon, the dark flow will remain one of astronomy's most tantalizing enigmas, a silent river flowing from the unknown. Rising from the heart of our galaxy like two colossal hourglasses of pure energy, the Fermi bubbles are one of the Milky Way's most dramatic hidden features. These twin lobes of scorching hot gas stretch 25,000 light-years above and below the galactic plane, so vast that if they were visible to the naked eye, they'd dominate the night sky, appearing 15 times wider than the full moon. But what makes them truly extraordinary isn't just their size, it's what they're made of. These bubbles glow with intense gamma radiation, the highest energy light in the universe, signaling violent events unfolding at energies we can barely fathom. The question is, what cosmic engine could have produced such monstrous structures? One leading theory points to our galaxy's supermassive black hole, Sagittarius, a star. Though quiet today, astronomers suspect it may have erupted in a cataclysmic feeding frenzy sometime in the past, perhaps as recently as a few million years ago. Picture a sleeping dragon suddenly waking to devour a passing star or gas cloud. The resulting explosion would have blasted jets of plasma outward at near light speed, inflating these enormous bubbles like cosmic balloons. Supporting this idea are flickering X-ray echoes near the galactic center, ghostly ripples that might be relics of this ancient outburst. If true, the Fermi bubbles could be the Milky Way's scars from a long-ago temper tantrum, a reminder that even our relatively calm galaxy has a violent past. But there's a competing explanation that's even more exotic: dark matter. Some theorists propose these bubbles might be the aftermath of countless annihilations between invisible dark matter particles colliding near the galaxy's core. According to this idea, when these mysterious particles smash together, they obliterate each other in bursts of gamma rays, slowly building up the colossal structures we see today. It's a tantalizing thought. The Fermi bubbles could be the first visible evidence of dark matter's hidden interactions, a shadow universe making itself known through these glowing fingerprints. Yet both theories face hurdles. If Sagittarius, a star, was responsible, why don't we see similar bubbles in other galaxies with active black holes? And if dark matter is the culprit, why don't the bubbles show the symmetrical, smooth distribution most models predict? The truth might lie somewhere in between, perhaps a combination of black hole activity and particle physics we haven't yet untangled. What's clear is that the Fermi bubbles aren't just a galactic oddity, they're a portal into the most energetic processes shaping our cosmic neighborhood. Whether relics of a black hole's fury or whispers from the dark universe, they remind us that even our familiar Milky Way harbors secrets waiting to rewrite the textbooks. And with every new gamma-ray telescope we launch, we get closer to reading their explosive story. Deep in the cosmic nursery where galaxies are born, float the universe's most radiant enigmas, Lyman alpha blobs. These colossal clouds of hydrogen gas, some stretching hundreds of thousands of light years across, glow with an otherworldly intensity, bathing the cosmos in a specific shade of ultraviolet light known as Lyman alpha radiation. Imagine stumbling upon a neon sign in the middle of an empty desert, bright, inexplicable, and impossible to ignore. That's the sheer strangeness of these blobs. But what makes them truly remarkable isn't just their glow, it's what they're hiding inside, the fiery birthplaces of entire galaxies. These blobs act as cosmic maternity wards, where swirling gas cools and collapses into the seeds of future galaxies. Inside their luminous depths, stars ignite at rates hundreds of times faster than in our own Milky Way, creating stellar fireworks on a scale we can barely fathom. The most famous of these structures, SSA-22, is so vast that its light takes nearly 12 billion years to reach us, a snapshot of the universe in its rowdy teenage years, when galaxies were forming at breakneck speeds. Yet for all their brilliance, the source of their glow remains one of astrophysics' most stubborn puzzles. The leading theory suggests that the blobs shine due to a celestial domino effect. As young, hot stars burst to life within them, they flood the surrounding hydrogen gas with ultraviolet radiation. This energy excites the gas atoms, which then re-emit the light at the specific Lyman alpha wavelength, like a cosmic neon sign powered by starlight. But there's a catch. Some blobs glow far brighter than their star populations should allow. It's as if a single candle were lighting up an entire stadium. This discrepancy has led to wilder explanations, including the influence of supermassive black holes lurking in the blob's cores. As these black holes devour matter, they could unleash torrents of energy that ripple through the gas, supercharging its glow. Others propose that the blobs might be illuminated by cold streams of primordial gas left over from the universe's birth, raining down and igniting the hydrogen like gasoline meeting a spark. What's undeniable is that Lyman alpha blobs are more than just pretty lights. They're time capsules from an era when the universe was assembling its grand structures. By studying them, we're glimpsing the construction sites of cosmic cities, watching as gravity weaves scattered gas into the galaxies we recognize today. And with each new observation, we get closer to understanding why these glowing giants shine so fiercely and what secrets they still hold in their radiant depths. There's an invisible force in the universe playing tug of war with entire galaxies, and for decades we couldn't even see it. Hidden behind the thick dust of our own Milky Way's disk lies the Great Attractor, a gravitational monstrosity pulling thousands of galaxies, including our own, toward the constellation Centaurus at over 1 million miles per hour. It's as if the cosmos has tilted its head, and everything is sliding toward some unseen cosmic drain. But what makes this mystery even more frustrating is that we've been staring straight at it for most of human history and couldn't see past the galactic smokescreen. The Great Attractor's story begins with a paradox. In the 1970s, astronomers mapping the universe's large-scale motion noticed something bizarre. Galaxies weren't just drifting apart as the universe expanded. They were also streaming toward a specific point in space like iron filings drawn to a magnet. The problem, that point lay directly behind the densest part of our galaxy's plane, where interstellar dust blocks nearly all visible light. Imagine trying to study a bonfire through a blizzard. That's how obscured this region was. For years, the Great Attractor remained a ghost, its presence inferred only by the way it yanked galaxies off course. Breakthroughs in infrared and radio astronomy finally peeled back the veil. Instruments like NASA's WMAP and Planck satellites, designed to study the cosmic microwave background, inadvertently became our best tools for mapping this hidden leviathan. They revealed the Great Attractor isn't a single object but a dense knot of galaxies, a gravitational anchor weighing in at roughly 100 quadrillion times the mass of our Sun. Yet here's the twist: it's not massive enough to fully explain the observed motion. The math didn't add up, something even bigger had to be pulling us. Enter the Shapley supercluster, the universe's most colossal known structure at the time of its discovery. Lying 650 million light-years beyond the Great Attractor, this sprawling metropolis of galaxies exerts its own gravitational influence, effectively playing a cosmic game of keep away. Think of it as two giants locked in an arm wrestling match over the fate of our local universe, with the Great Attractor as the closer, visible contender, and Shapley as the distant powerhouse tilting the scales. Now the plot thickens. Recent surveys suggest neither structure alone can fully account for the observed flow of galaxies. There might be something even more massive, something beyond Shapley, tugging at the cosmic web. This realization has sent astronomers scrambling to map the universe's large-scale flows in unprecedented detail, tracing the invisible rivers of dark matter that guide everything we see. The Great Attractor isn't just a curiosity, it's a lesson in cosmic humility. It reminds us that even when we think we've mapped the heavens, the universe keeps its greatest secrets just out of sight, waiting for the right tools, the right moment to reveal them. And as our telescopes grow sharper, who knows what other titans might emerge from the shadows? The Phoenix cluster should be a cosmic graveyard, a place where gas cools so rapidly it ought to collapse into a silent, starless void. But when astronomers trained their telescopes on this behemoth 1.2 billion light-years away, they found the opposite, a storm of star birth so intense it defies everything we thought we knew about how galaxy clusters evolve. At its heart lies not a dormant monster, but a supermassive black hole caught in a delicate dance, one that's simultaneously pouring energy into the cluster while allowing cold gas to rain down in dazzling, contradictory abundance. This isn't just a cluster, it's a cosmic paradox playing out on a scale so vast it's rewriting astrophysics textbooks. For decades, the cooling flow problem haunted theorists. Galaxy clusters like Phoenix sit immersed in oceans of superheated gas plasma, so scorching it glows in X-rays. Basic physics says this gas should cool over time, sinking toward the cluster's center like mist settling in a valley. Early models predicted these cooling rivers would fuel unstoppable waves of star formation, creating galaxies so dense they'd outshine entire constellations. But when astronomers looked, they found clusters suspiciously quiet. Where was all that cold gas going? The answer seemed to lie in the supermassive black holes at these clusters' cores. As gas drifted inward, theorists assumed the black holes would awaken in furious outbursts, their jets blasting energy back into the system like cosmic blowtorches, reheating the gas and shutting down cooling entirely. Then came Phoenix. Observations from the Chandra X-ray Observatory revealed gas cooling at a rate of 4,000 suns worth of material per year, the fastest ever recorded. Yet instead of triggering the expected feedback loop where the central black hole erupts to halt cooling, Phoenix's core was oddly restrained. Its black hole seemed to be whispering rather than shouting, emitting gentle pulses of energy that somehow allowed cooling and star formation to proceed at breathtaking scales. Here was a cluster breaking all the rules, its gas condensing into newborn stars at rates hundreds of times faster than in our own Milky Way. The cluster's core shone with the blue light of countless massive young stars, a sight so unexpected one astronomer compared it to finding a rainforest thriving in the middle of a desert. The secret might lie in Phoenix's unique balancing act. While most cluster black holes erupt in violent, sporadic outbursts, Phoenix's appears to be feeding steadily like a slow-burning furnace. This steady trickle of energy may prevent the gas from overheating while still allowing pockets to cool just enough to form stars. It's a Goldilocks scenario, not too hot, not too cold, but just right for star making on an industrial scale. Supporting this idea are stunning Hubble images showing delicate filaments of cold gas weaving through the cluster like ribbons, each one a potential stellar nursery in the making. But Phoenix isn't just challenging old theories, it's offering a glimpse into the universe's most extreme environments. Some scientists speculate we might be witnessing a rare phase of cluster evolution, one that most galaxies experience only briefly before their black holes awaken fully. Others wonder if Phoenix's black hole is fundamentally different, its jets angled in a way that permits cooling along certain channels while heating others. What's certain is that this cluster forces us to reconsider the complex interplay between gravity, thermodynamics, and black hole behavior on scales we're only beginning to map. As telescopes grow more powerful, the Phoenix cluster stands as a reminder that the universe loves to defy our neat categorizations. Just when we think we've unraveled one cosmic mystery, another rises from the ashes, reshaping our understanding of how the most massive structures in existence live, breathe, and forge the elements that make our very existence possible. At first glance, the Red Rectangle Nebula looks like something straight out of a geometry textbook. A glowing, crimson-hued X suspended in space, framed by nested rectangles so precise they seem drawn with celestial rulers. Located about 2,300 light-years away in the constellation Monoceros, this stunning proto-planetary nebula defies the usual chaotic beauty of dying stars. Instead of billowing clouds or twisting tendrils, it presents an almost architectural symmetry, a puzzle that's captivated astronomers since its discovery in the 1970s. But what could sculpt such perfection in the turbulent final throes of a star's life? The answer might lie in an intricate cosmic ballet between twin stars and their swirling debris. The Red Rectangle's mesmerizing structure starts with its central engine, a binary star system where one star has already shed its outer layers while its companion remains intact. As the dying star expels gas and dust into space, the gravitational tug of war between the two stars molds this material into a thick disk, like a spinning record made of stardust. But here's where things get fascinating. If we were viewing this disk face-on, it might look ordinary. Our perspective, however, is nearly edge-on, turning this seemingly simple setup into a cosmic shadow puppet show. The dense disk blocks light from the central stars, casting twin cones of shadow that carve out the nebula's iconic X shape. Meanwhile, the rectangular frame likely comes from shockwaves where faster stellar winds collide with slower-moving material ejected earlier, a bit like waves crashing against a seawall and spraying outward in perfect right angles. Yet even this elegant explanation doesn't account for all the Red Rectangle's quirks. Its rich red hue, for instance, comes from a type of organic molecule called polycyclic aromatic hydrocarbons complex carbon chains that thrive in the nebula's unique conditions. These molecules are nicknamed star stuff, and they're the same building blocks that, elsewhere in the universe, could seed the chemistry for life. How they formed here in such abundance is another mystery. Some researchers speculate the binary stars' interactions create ideal cosmic labs for these molecules to assemble, while others propose ultraviolet light from the stars is methodically breaking down and reforming the carbon chains like a celestial assembly line. Then there's the nebula's eerie stability. Most planetary nebulas change visibly over mere decades as their gas expands and dissipates, but the Red Rectangle has remained stubbornly unchanged since we first observed it. This could mean we're catching it at a rare, fleeting moment of equilibrium like a soap bubble frozen mid-pop, or that its binary stars are somehow regulating the outflow with precision. Future observations might reveal whether the nebula's geometry is a temporary masterpiece or a longer-lasting cosmic oddity. What makes the red rectangle truly special isn't just its beauty, but the way it challenges our assumptions. We expect dying stars to fade in chaos, not in razor-sharp geometry. Yet here, against all odds, nature has crafted a structure so precise it feels almost intentional. A reminder that the universe's artistry extends far beyond what we've yet imagined. And as we study its nested angles and crimson glow, we're not just seeing a nebula, we're glimpsing the hidden physics that can turn stellar death into a fleeting work of mathematical perfection. The cosmic microwave background should be a near-perfect thermal snapshot of the infant universe, a uniform globe bathing all of space. But one patch in the constellation Eridanus breaks this rule with chilling defiance. Known as the CMB cold spot, this region measures 70 microkelvins cooler than its surroundings, a temperature dip so statistically unlikely that astronomers calculate the odds at 1 in 200. It's as if someone took a cosmic ice cube and pressed it against the fabric of the universe, leaving behind a ghostly imprint that refuses to fade. Initial explanations pointed to a supervoid, a vast empty region where the absence of galaxies and matter could subtly distort the CMB photons passing through. Imagine light climbing out of a gravitational well, losing energy and cooling in the process, a phenomenon known as the integrated Sachs-Wolf effect. But when astronomers mapped the area, they found only a modest void capable of accounting for a fraction of the observed cooling. The numbers didn't add up. This left scientists staring at two possibilities. Either our understanding of cosmic voids is fundamentally incomplete, or the cold spot represents something far stranger. Enter cosmic texture, a theoretical defect in spacetime itself. According to certain grand unified theories, the early universe may have undergone phase transitions as it cooled, like water freezing into ice but on a cosmic scale. These transitions could have left behind wrinkles in spacetime, regions where the fabric of reality is knotted differently. If such a texture exists within the cold spot, it would warp the CMB photons passing through it, creating precisely the kind of temperature anomaly we observe. It's a tantalizing thought that we might be looking at a fossilized imprint from the universe's first trillionth of a second, a time when the forces of nature were still merging into their present forms. Then there's the most speculative explanation of all, a collision with a parallel universe. Some models of multiverse theory suggest that our cosmos could have bumped into another bubble universe during inflation, leaving behind a thermal bruise in the CMB. While this idea sits firmly at the edge of testable physics, it highlights how deeply the cold spot challenges our frameworks. When even exotic theories struggle to explain an observation, science knows it's onto something profound. What makes the cold spot especially compelling is its resistance to simple categorization. Unlike most cosmic anomalies, it refuses to yield to any single explanation, dangling just out of reach like a puzzle designed to humble us. Future galaxy surveys and precision CMB measurements may yet tilt the scales toward one theory or unveil something entirely unexpected. Until then, this enigmatic cold patch remains one of cosmology's most stubborn open questions, a whisper from the universe's dawn that we're still learning how to hear. Right now, two cosmic titans are locked in a slow-motion dance of destruction, one that will rewrite the night sky forever. The Andromeda Galaxy, our closest spiral neighbor, isn't just approaching the Milky Way. It's hurtling toward us at 250,000 miles per hour, pulled by gravity's irresistible grip. 4 billion years from now, these galaxies will collide in a spectacle that would leave any hypothetical future astronomers breathless. But this won't be the violent crash it sounds like. Instead, imagine two vast crowds passing through each other where individuals rarely touch, but the collective chaos transforms everything. The first signs will be subtle. As Andromeda looms closer, its spiral arms will stretch and distort under tidal forces, threading luminous rivers of stars across the heavens. These tidal tails will arc millions of light years into intergalactic space, glowing with newborn stars as colliding gas clouds trigger stellar fireworks. The Milky Way's familiar disk will warp into a splintered mess, its orderly spiral unraveling like a shattered vinyl record. Yet amid this apparent chaos, direct star-on-star collisions will be astonishingly rare. Despite billions of stars in each galaxy, space is so vast that stellar distances average 3 light-years apart, like tossing a handful of sand into an Olympic-sized pool and expecting grains to hit. What's truly at risk isn't stars, but the delicate architecture of both galaxies. As their mutual gravity rips through their structures, supermassive black holes at their cores, Sagittarius, a star in the Milky Way, and Andromeda's even larger P2 will begin a spiraling death spiral. Over billions of years, they'll whip through shredded galactic remains, flinging stars into chaotic orbits before finally merging in a gravitational wave burst detectable across the universe. Meanwhile, interstellar gas clouds will slam together, igniting hyperactive star-forming regions that could outshine entire galaxies today. The aftermath. A single, bloated elliptical galaxy, dubbed Milkdromeda by astronomers where our solar system, if it survives, will orbit a new galactic center far from its birthplace. Night skies would glow with the combined light of 2 merged galaxies, strewn with the fading embers of this cosmic reunion. But here's the twist: this collision isn't unique. Galactic mergers shaped the universe we see today, from the Milky Way's own cannibalized dwarf galaxies to the behemoths we observe in deep space. We're just lucky enough to live at the perfect moment to foresee our own fate, a front-row seat to the universe's relentless, beautiful demolition. The Bullet Cluster isn't just a cosmic collision, it's a smoking gun. When astronomers first studied this titanic clash of galaxy clusters 1.4 billion light-years away, they expected chaos. What they found instead was a revelation so profound it settled one of astronomy's fiercest debates. Dark matter is real, and here was the proof written across the sky in twisted starlight. Picture 2 galaxy clusters, each containing hundreds of galaxies slamming into each other at millions of miles per hour. The violence of this impact should have scrambled everything, leaving behind a messy soup of gas, stars, and whatever invisible ingredients lurk in cosmic shadows. But the Bullet Cluster had other plans. Thanks to a brilliant combination of X-ray and gravitational lensing observations, scientists spotted something extraordinary. The visible matter and the invisible mass had gone their separate ways, like oil and water refusing to mix. Here's how it happened. As the clusters collided, their hot gas clouds filled with ordinary matter piled up in the center, creating a shockwave so intense it glowed in X-rays. But their dark matter, that kept right on moving, undisturbed. How do we know? Because even though we can't see dark matter directly, its gravitational grip bends the light from more distant galaxies behind it, creating eerie, stretched mirages called gravitational lenses. By mapping these distortions, astronomers traced the dark matter's location, and it wasn't where the gas was. It had sailed straight through the collision like a ghost, leaving the visible material behind. The implications were earth-shaking. If dark matter interacted like normal matter, it would have slowed down and stayed with the gas. The fact that it didn't meant only one thing: dark matter doesn't play by the same rules. It ignores electromagnetism, doesn't emit or absorb light, and barely even notices ordinary matter exists. The Bullet Cluster became the first direct evidence that this enigmatic substance wasn't just a mathematical trick, it was a tangible, physical reality shaping the cosmos. But the surprises didn't stop there. The cluster's bullet shape, a dense subcluster punching through like a cosmic projectile, revealed dark matter's distribution in unprecedented detail. Unlike gas, which heats up and slows down, the dark matter's trajectory showed it was more like a swarm of bees moving together, barely affected by the collision. This behavior hinted that dark matter might be cold, slow-moving and clumpy, rather than fast, and diffuse a crucial clue for understanding how galaxies formed in the early universe. Yet for all its clarity, the bullet cluster also deepened the mystery. Why doesn't dark matter interact with itself? Are there multiple types of dark particles? Every answer this collision provided seemed to spawn new questions, proving once again that the universe's greatest discoveries don't just solve puzzles, they rewrite them. And as telescopes grow sharper, who knows what other cosmic crime scenes might reveal about the invisible skeleton holding our universe together. The Whirlpool Galaxy spins in perfect cosmic harmony with its smaller partner, NGC 5195, but this celestial dance is anything but gentle. Over the past 300 million years, their gravitational tug-of-war has sculpted M51's breathtaking spiral arms into the iconic whirlpool we see today. Each close encounter sends shockwaves through clouds of gas and dust, igniting bursts of star formation so intense they're visible across 23 million light-years of space. This isn't just a pair of galaxies passing in the night. It's a slow-motion collision that's rewriting both their destinies. Hubble's razor-sharp images reveal the drama in stunning detail. As NGC 5195 swings past the whirlpool's outer disk, its gravity grabs hold of loose material, stretching it into luminous tidal bridges that glow with newborn stars. These bridges aren't static, they shift and ripple with each orbital pass like ribbons caught in a cosmic breeze. One particularly spectacular filament, dubbed the umbilical cord, visibly connects the two galaxies, funneling gas from the smaller companion back into the whirlpool star-forming factories. It's a galactic bloodline feeding the larger galaxy with fresh stellar fuel. What makes this duo extraordinary isn't just their beauty, but the clarity of their life cycle. Unlike messy galactic mergers that obscure their history, M51 and its companion are locked in a predictable rhythm. Astronomers have reconstructed their orbits like celestial choreography, tracing how the smaller galaxy first plunged through the whirlpool's disk roughly 500 million years ago, then looped back around for another pass. Each approach triggers fireworks, dense pockets of gas collapse under gravitational stress, birthing massive star clusters that blaze with blue-white intensity before exploding as supernova. These explosions carve glowing cavities in the gas clouds, leaving behind bubble-shaped relics of past stellar generations. Yet the real marvel lies in the feedback loop they've created. As young stars die violent deaths, their explosions enrich surrounding gas with heavy elements, seeding future stars with the building blocks for planets and potentially life. Meanwhile, NGC 5195 isn't just a passive donor, it's being transformed too. The whirlpool's gravity has stripped away its outer layers, leaving a distorted core shrouded in dust lanes that twist like scars from the encounter. This gravitational tango offers more than just a light show. It's a masterclass in galactic evolution. By studying how these two galaxies exchange matter and energy, scientists gain insights into how all spirals, including our Milky Way, grow and change over eons. And with the next close pass estimated in another 50 million years, the show is far from over. The whirlpool and its companion will keep reshaping each other until, billions of years from now, they finally merge into something entirely new, proving that even in the vastness of space, no galaxy is an island. The Sombrero Galaxy wears its mysteries like the broad rim of its namesake hat, elegant, dramatic, and hiding surprising depths beneath its brim. Officially catalogued as M104, this cosmic marvel floats 28 million light-years away in the constellation Virgo, presenting astronomers with a celestial riddle. At first glance, it looks like a classic spiral galaxy seen edge-on, its dust lanes slicing across a glowing disk, but peer closer and contradictions emerge. Its core swells with a dense, star-packed bulge typical of elliptical galaxies, while its outer regions host the precise, delicate structure of a spiral. This isn't just a galaxy, it's a cosmic chimera, challenging our neat classifications and hinting at a violent past that reshaped its very identity. What makes the sombrero's dual nature even more intriguing is its staggering metal content, specifically within its globular clusters. These ancient, dense spheres of stars orbit the galaxy like swarms of fireflies, usually containing some of the universe's most pristine, metal-poor stars. Yet the sombrero's clusters blaze with heavy elements like iron and magnesium, as if someone sprinkled stardust into these primordial time capsules. One explanation points to a history of galactic cannibalism. The sombrero may have devoured smaller, gas-rich galaxies long ago, their digested remains enriching these clusters with metals through successive generations of stars. Supporting this theory is the galaxy's unusually large population of globular clusters, nearly 2,000 compared to the Milky Way's paltry 150, a telltale sign of past mergers. Then there's the matter of that unmistakable bulge. Spanning half the galaxy's visible light, this central orb contains stars moving in chaotic, randomized orbits, a hallmark of ellipticals. But how does a galaxy retain such a disordered core while maintaining pristine spiral arms? The answer might lie in a rare event, a near-miss collision with another massive galaxy billions of years ago. Simulations show such encounters can gravitational shockwaves that funnel gas toward the center, triggering bursts of star formation that puff up the bulge while leaving the outer disk intact. Infrared observations reveal the sombrero's bulge is indeed laced with younger stars, suggesting it underwent exactly this kind of violent rejuvenation. But the sombrero's surprises don't stop there. Its dust ring, that iconic dark lane circumnavigating its midsection, isn't just a passive accessory. Radio telescopes have detected vast reservoirs of molecular hydrogen gas here, the raw material for new stars. Yet curiously, the ring shows little star-forming activity. This quietude hints at another mystery. The galaxy's supermassive black hole, weighing in at nearly 1 billion solar masses, might be suppressing star birth through intense radiation or jets, effectively placing the entire disk on cosmic lockdown. Every observation peels back another layer of this galactic enigma. Is the sombrero a spiral that aged prematurely, an elliptical disguised by a borrowed disk, or something entirely unique forged in a forgotten chapter of cosmic history? For now, it remains a masterclass in galactic ambiguity, a reminder that the universe often resists simple labels, preferring instead to dazzle us with exceptions to every rule. The supermassive black hole at the heart of Galaxy M87 isn't just any cosmic beast, it's the first one humanity ever saw with our own eyes, or more accurately, through the collective gaze of the Event Horizon Telescope's planet-sized array. That now iconic image from 2019 didn't just confirm what theorists had long predicted. It handed us a smoking gun for Einstein's general relativity while dangling new mysteries we're still scrambling to solve. At 55 million light-years away and weighing in at 6.5 billion times our sun's mass, this black hole's shadow, a dark void ringed by a fiery crescent of light, should have been symmetrical. Instead, it glared back at us with a lopsided brilliance that's rewriting the rules of extreme physics. That asymmetry is the key. The glowing crescent comes from photons whipping around the black hole's event horizon at near light speed. Their paths bent so violently they form a halo around the point of no return. General relativity predicted this photon ring, but the brightness imbalance caught even seasoned physicists off guard. The southern part of the ring blazes noticeably brighter than the northern segment, a telltale sign of relativistic beaming, where light from material moving toward us gets boosted while receding material dims. This means the entire accretion disk isn't just spinning, it's likely tilted at a drastic angle, warped by the black hole's immense gravity into a chaotic vortex. Imagine a record player warped so badly the needle keeps jumping, except here, the needle is superheated plasma moving at nearly light speed, and the record is space-time itself. But M87's black hole had another surprise up its sleeve, its monstrous relativistic jet. Stretching 5,000 light-years into space, this pencil-thin beam of plasma moves at 99% light speed, punching through intergalactic space like a cosmic blowtorch. For decades, astronomers assumed such jets formed when tangled magnetic fields near the black hole's poles funneled material outward. The EHT's follow-up observations revealed something more nuanced. Polarized light studies showed the jet's base aligns with twisted magnetic field lines not just near the poles but across the entire accretion disk. It's as if the black hole is spinning so fast it's dragging space-time around with it, twisting magnetic fields into a spring-loaded launch system for that incredible jet. What makes these discoveries revolutionary isn't just their confirmation of existing theories, but their contradictions. The jet's stability defies models predicting it should wobble like a spinning top, while the shadow's size perfectly matches relativity's predictions despite the disk's extreme turbulence. This paradox suggests black holes operate with an eerie precision amid their chaos, balancing ferocious energy output with gravitational order in ways we're only beginning to decode. Every new observation peels back another layer, revealing not just how black holes devour matter, but how they shape entire galaxies with their explosive whispers and silent shadows. The antennae galaxies aren't just colliding, they're exploding with creation. As these two spirals tear through each other 220 million light-years away, their violent embrace has ignited one of the most intense starbursts ever recorded, birthing over 100 superstar clusters in a dazzling display of cosmic fertility. Each of these clusters packs the firepower of 1,000,000 suns, crammed into regions no larger than a few dozen light-years across. To put that into perspective, if our own Orion Nebula, one of the Milky Way's most prolific stellar nurseries, stood next to these clusters, it would look like a candle beside a bonfire. This isn't just star formation, it's star formation turned up to 11, a celestial fireworks show where the sparks are newborn suns. What makes this collision so spectacular isn't just the sheer number of stars being born, but the frenzied pace at which it's happening. The antennae's star formation rate clocks in at a staggering 50 times that of our Milky Way, with enough gas and dust being converted into stars every year to build 20 solar systems like ours. Hubble's sharp eye reveals why. As the galaxy's gravitational forces pull and twist their spiral arms, vast clouds of hydrogen slam together like storm fronts, collapsing under their own weight into seething stellar factories. Infrared telescopes peer through the dust to show these regions glowing white-hot, so dense with young stars that their combined light outshines entire galaxies. Yet this brilliance comes at a cost. Many of these newborn stars are monstrous dozens of times heavier than our Sun and destined to live fast and die young in spectacular supernova. Their explosions will scatter heavy elements like oxygen and iron back into the galactic winds, enriching future generations of stars and planets. But they'll also blast away surrounding gas, eventually starving the galaxies of the raw material needed to keep the party going. This self-destructive cycle is why starbursts like the antennae are fleeting by cosmic standards, lasting just a few 100 million years before sputtering out. The end game here is just as fascinating as the present chaos. Simulations show the antennae's long, streaming tidal tails. Those iconic antennae stretching across space will eventually fall back toward the galactic core, merging into a single, bloated elliptical galaxy. Unlike the elegant spirals they once were, this new galaxy will be a featureless sphere of aging stars, its gas reserves depleted and its star-forming days long over. But hidden in its haze of ancient suns will be the fossilized remains of this violent starburst, those 100 superstar clusters, now globular clusters, orbiting like silent witnesses to the collision that birthed them. What we're seeing right now is a cosmic rarity, a snapshot of two galaxies caught mid-transformation, rewriting their destinies in real time. For astronomers, the antennae offer a front-row seat to understanding how all elliptical galaxies may have formed through similar cataclysmic mergers in the universe's youth. And for the rest of us, they're a breathtaking reminder that even in destruction, the universe finds a way to create. The cartwheel galaxy spins through space like a cosmic dartboard frozen mid-throw, its perfect concentric rings telling the story of one of the most violent galactic collisions ever witnessed. About 500 million years ago, a mere blink in cosmic time, a smaller galaxy plunged straight through this spiral's heart at nearly 200,000 miles per hour. The impact sent shockwaves rippling outward through interstellar gas like pebbles dropped in a pond, triggering waves of star formation that froze in time as luminous blue rings. What we're seeing isn't just a galaxy, it's a celestial crime scene, with each glowing ring marking another chapter in this gravitational whodunit. Hubble's razor-sharp vision reveals the aftermath in stunning detail. The innermost ring, a dense circle of newborn stars just 1,500 light-years from the core, blazes with the intensity of 1,000 Orion nebulas. Further out, a second ring, the galaxy's original spiral arms stretched and shattered by the collision, glows with slightly older stars, their blue hue fading to yellow as they age. Beyond that lies the most spectacular feature, an outer ring 3 times the Milky Way's diameter, where the collision's shockwave compressed gas clouds so violently it ignited a firestorm of starbursts. This outermost ring currently spawns stars at 20 times the rate of our entire galaxy, its brilliance visible across 150 million light-years of space. But where's the intruder? Astronomers have scoured the cartwheel's surroundings and found not one but 2 suspect galaxies. One shows clear signs of gravitational distortion, tidal tails stretching behind it like cosmic breadcrumbs, while the other appears unscathed. The leading theory suggests a game of celestial billiards. The first galaxy likely blasted through the cartwheel's center, then swung around for a second collision before being flung away, while the second may have been a bystander caught in the gravitational chaos. Supporting this idea are faint stellar streams arcing through the scene, ghostly trails of stars ripped from their parent galaxies during the violent encounter. What makes the cartwheel truly remarkable is how it defies expectations. Standard models predicted such rings should fade within 300 million years as star formation exhausts the available gas. Yet here it shines 500 million years later with no signs of stopping. The secret may lie in the galaxy's unique structure. Its hollow center acts like an echo chamber for star formation, with each wave compressing gas farther out while fresh material falls inward to replenish it. X-ray observations reveal another clue: the galaxy's core hosts not 1 but 2 supermassive black holes, suggesting the intruder may have left part of itself behind during the collision. As we watch these ripples propagate through space, we're witnessing more than just destruction, we're seeing creation on a galactic scale. The same forces that tore the cartwheel apart are now rebuilding it, forging new stars, planets, and perhaps even the ingredients for life from the ashes of chaos. It's a cosmic phoenix in slow motion, reminding us that even in the vastness of space, no catastrophe is ever truly the end, just the beginning of something new. Wrapped around our Milky Way like a celestial serpent, the Boötes Roman 3 stellar stream slinks through space, a ghostly river of stars whispering secrets about our galaxy's violent past. This fragmented trail of ancient suns, discovered in 2019, isn't just another stellar oddity. It's the shredded remains of a dwarf galaxy that ventured too close to the Milky Way's gravitational embrace. Stretching over 30,000 light-years across our galactic halo, this stream's delicate structure and chaotic orbit offer something rare, a forensic snapshot of how galaxies grow by devouring their smaller neighbors, and a chance to map the invisible dark matter scaffolding that guides the entire cosmic feast. Most stellar streams form when globular clusters get stretched apart by tidal forces, but Boötes Roman 3 is different. Its stars bear the chemical fingerprints of a dwarf galaxy, metal poor and primordial, forged in the early universe before heavy elements were commonplace. Their trajectories suggest this wasn't a slow disintegration, it was a catastrophic encounter. Imagine a small galaxy, perhaps 1/10 the Milky Way's mass, plunging through our galaxy's outskirts at a steep angle. As it looped around, the Milky Way's gravity peeled away stars with each pass, scattering them along decaying orbits until only this wispy stream remained a cosmic crime scene where the victim's outline is still visible in the debris. But Boötes' Roman 3 real value lies in what it reveals about the dark matter halo surrounding our galaxy. Unlike visible matter, which concentrates in the Milky Way's disk, dark matter forms an enormous spherical cloud permeating everything. Its gravitational pull dictates how streams like Boötes' Roman 3 move, but because we can't see dark matter directly, these streams become our only way to trace its distribution. Here's the breakthrough. Boötes' Roman 3 stars aren't moving as predicted. Their paths wiggle and twist in ways that suggest the dark matter halo isn't smooth, it's lumpy, possibly clumped around smaller sub-halos left over from the universe's formation. Think of it like tossing confetti into a fan. If the airflow were perfectly even, the confetti would drift uniformly. But if the airflow has hidden eddies, the confetti swirls unpredictably. Boötes' Roman 3 stars are that confetti, and their dance reveals the unseen currents of dark matter. The stream's bizarre width adds another layer to the puzzle. Most tidal streams are narrow, like ribbons unspooled by gravity. Boötes' Roman 3, by contrast, fans out into a diffuse band, hinting that the original dwarf galaxy might have been unusually puffy, or that dark matter's gravitational kicks scattered its stars more violently than models predict. Some astronomers even speculate the dwarf galaxy might have been incredibly dark matter-rich itself, amplifying the chaos as it disintegrated. Every deviation from expectation is a clue, a breadcrumb leading us closer to understanding how dark matter shapes galaxy evolution. What makes Boötes' Roman 3 especially thrilling is its persistence. Most streams dissolve into the galactic background after a few orbits, but this one has clung to its identity for billions of years, a testament to how carefully the cosmos preserves its destruction. As telescopes like Rubin Observatory and Euclid come online, they'll map Boötes' Roman 3 stars in unprecedented detail, turning this stellar river into a high-precision tool for probing the Milky Way's hidden architecture. It's a reminder that even in the wreckage of cosmic collisions, there are stories waiting to be read if we know how to listen. Stretching nearly 600,000 light-years across our galactic backyard, the Magellanic Stream is a cosmic river of gas so vast it could wrap around the Milky Way 5 times over. This shimmering filament of hydrogen, glowing faintly in radio wavelengths, arcs across the southern sky like a celestial bridge between the large and small Magellanic Clouds, our galaxy's 2 largest satellite galaxies, and the Milky Way itself. But this isn't just a pretty cosmic feature. It's the shredded remains of a gravitational tug of war that's been raging for billions of years, and its fate may determine the next chapter of star formation in our own galaxy. The origin story of this gargantuan ribbon reads like a cosmic thriller. For decades, astronomers assumed the stream formed through tidal stripping, the relentless gravitational pull of the Milky Way slowly unraveling the Magellanic Clouds as they orbit us, like a spider spinning silk from trapped flies. But newer observations reveal a twist. The clouds might be tearing themselves apart. As they dance around each other in a tight binary orbit, their mutual gravitational forces could be ripping gas away in violent surges, creating this sprawling stellar slipstream. Supporting this idea are shock fronts and kinks in the stream's structure, signs of messy, chaotic interactions rather than the smooth, unraveling tidal theory predicts. Then there's the wild card, ram pressure stripping. As the Magellanic Clouds plow through the Milky Way's diffuse halo of hot gas, they might be leaving behind a wake of stripped material, like a speedboat churning up water. X-ray telescopes have detected patches of the stream heated to millions of degrees, exactly what you'd expect if superheated galactic plasma were colliding with cooler cloud gas. This could mean the stream isn't just one thing, but a hybrid, part tidal debris, part pressure-cooked fallout. But the real magic lies in where the stream is headed. Right now, this river of gas is on a collision course with the Milky Way's disk, and when it hits likely within the next few 100 million years, it could trigger a fireworks display of starbirth. Simulations show the stream's gas is rich in the heavy elements needed to forge new stars and planets, making it prime cosmic real estate for future stellar nurseries. Some astronomers even speculate it might already be feeding hidden star-forming regions in our galaxy's outer fringes, quietly seeding the next generation of suns. Yet the stream's full story is still coming into focus. Recent measurements suggest it contains more mass than the Magellanic Clouds themselves, raising the bizarre possibility that we're seeing not just stripped gas, but an entire invisible dark matter structure dragging material along with it. Others argue the stream could be laced with primordial gas from the early universe, offering a rare sample of pristine matter untouched by stellar furnaces. Every new observation peels back another layer of this cosmic mystery, revealing a dynamic system where gravity, pressure, and time intertwine. And as radio telescopes like the Square Kilometre Array come online, they'll trace the stream's faintest tendrils in unprecedented detail, helping us decode whether this celestial river is a relic of destruction, a harbinger of creation, or both. One thing's certain, the Magellanic Stream isn't just a shadow from the past. It's a living, evolving bridge between galaxies, and its currents may yet shape the future of our own. Hanging above the Milky Way's disk like a cosmic smudge, the Virgo overdensity defies easy explanation. This sprawling swarm of stars, first spotted in 2005, blankets a stunning 5,000 square degrees of sky, so vast it spills beyond the constellation Virgo into neighboring Libra and Serpens. At first glance, it looks like just another patch of the night sky, but peer deeper, and the numbers don't add up. This region contains nearly 30% more stars than it should, a stellar excess so pronounced that astronomers still debate whether we're seeing the ghostly remains of a devoured dwarf galaxy or the Milky Way's own spiral arms reaching farther than we ever imagined. One camp argues the overdensity is a galactic fossil, the shredded corpse of a dwarf galaxy torn apart by our Milky Way's gravity. Supporting this idea are the stars themselves, many rich in alpha elements like magnesium and titanium, a chemical signature typical of ancient, low-mass galaxies that formed stars quickly and died young. If true, the overdensity could be the last visible traces of a victim in the Milky Way's long history of galactic cannibalism, its stars scattered across the halo like crumbs from a cosmic feast. The clincher, some stars here move together in coherent streams, like survivors huddling after a shipwreck, exactly what you'd expect from a disrupted satellite galaxy. But there's a twist. Other measurements reveal stars in the overdensity with wildly different velocities and chemistries, as if they were born in separate places and later thrown together by chance. This has led to a radical alternative. Perhaps we're not looking at an intruder at all, but at a part of the Milky Way itself. Specifically, the overdensity might be the outermost reaches of our galaxy's disk, warped and twisted by gravitational interactions with passing galaxies or dark matter subhalos. Picture a spinning pizza dough flung slightly off-kilter somewhere along the way. The Milky Way's outer disk may have gotten tugged out of alignment, leaving this overdense ripple in its wake. The most tantalizing clue comes from stellar orbits. While some stars in the overdensity trace looping, halo-like paths typical of captured galaxies, others follow nearly circular orbits aligned with the Milky Way's disk, strong evidence they've always belonged here. This duality has sparked a hybrid theory. Maybe the overdensity is both things at once. A dwarf galaxy could have collided with the Milky Way's outer disk long ago, its stars mingling with native disk stars until the two populations became indistinguishable. It's like finding an ancient ship buried in a harbor after centuries. The wood of the wreck and the planks of the docks merge into a single structure, their origins blurred by time. Unraveling this mystery isn't just academic. If the overdensity is a disrupted dwarf, its stars could help map the Milky Way's dark matter halo, their orbits tracing the invisible gravitational contours like iron filings around a magnet. If it's a warped disk, it reveals how fragile galactic structures are, bending under forces we've yet to fully understand. Either way, this celestial puzzle reminds us that even our home galaxy hides surprises in its shadowy outskirts, waiting for sharper telescopes and sharper minds to bring them into focus. We might be floating inside one of the universe's most colossal empty spaces, a cosmic bubble so vast it could rewrite our understanding of the cosmos. Welcome to the KBC Void, a staggering 2 billion light-year wide underdensity where galaxies are eerily scarce, and by sheer cosmic coincidence, we seem to be sitting almost exactly at its center. This isn't just an interesting quirk of our cosmic address. It's a potential game changer for how we measure the universe's expansion and whether we've been misinterpreting one of astronomy's most critical numbers, the Hubble constant. The KBC Void, named after astronomers Keenan, Barger, and Cowie, who identified it in 2013, isn't your run-of-the-mill cosmic hole. While voids like the Boötes Void span hundreds of millions of light-years, this one dwarfs them all, stretching across roughly 7% of the observable universe. Inside this bubble, matter is about 20% sparser than the cosmic average, meaning galaxies here are fewer and farther between. That might not sound dramatic, but on these scales, even slight density variations can warp our perception of reality. Here's why. When we measure how fast the universe is expanding, we assume we're in a fairly average neighborhood. But if we're actually inside a gigantic underdense region, gravity's weaker pull here could make distant galaxies appear to be fleeing faster than they really are, throwing off our calculations like a misaligned compass. This could explain one of cosmology's most stubborn headaches, the Hubble tension. For years, two methods of measuring the universe's expansion rate have disagreed. Observations of nearby supernova and Cepheid variables suggest a faster expansion rate, while studies of the cosmic microwave background point to a slower one. The gap might seem small, but in a field where precision is everything, it's a glaring inconsistency. The KBC Void offers a tantalizing solution. If we're inside a bubble, local measurements could be skewed by our unusual environment, while the CMB, which reflects the universe's overall structure, remains unaffected. It's like trying to judge ocean currents while unknowingly floating in a whirlpool. Your measurements would depend entirely on where you stood. But here's the catch: being at the center of such a void is astronomically improbable, raising eyebrows among skeptics. If the void were real but offset from our position, its effects would be less pronounced, making this perfect alignment statistically suspicious. Some researchers argue we might be seeing a measurement artifact or a flaw in how we model galaxy distributions. Others propose an even wilder idea. The void isn't a fluke but a signature of exotic physics, like a remnant of early universe inflation or the gravitational footprint of a parallel universe. The debate hinges on two questions: is the void real, and is it big enough to impact the Hubble constant? Recent galaxy surveys hint at its existence, but the data isn't conclusive. Upcoming projects like the Rubin Observatory's Legacy Survey of Space and Time aim to settle the matter by mapping millions of galaxies in unprecedented detail. Until then, the KBC Void remains a ghostly possibility, a reminder that even our grandest cosmic theories might be filtered through the lens of our accidental and perhaps extraordinary place in the universe. Whether it's a statistical mirage or a key to unlocking deeper mysteries, one thing is clear: the cosmos still has ways to humble us, revealing how much we don't know about the vast stage on which we float. Dragonfly 44 isn't just a galaxy, it's a cosmic paradox, stretching across the sky like a ghostly smear in the constellation Coma Berenices. This Milky Way-sized behemoth emits barely 1% of the light our own galaxy does. If you swap the Milky Way for Dragonfly 44 in our night sky, you'd struggle to see it at all. Yet despite its ethereal appearance, this galaxy holds a staggering secret. It moves as if anchored by something colossal, something invisible. The culprit, a monstrous halo of dark matter, outweighing its visible stars by a ratio of 10,000 to 1. This isn't just a galaxy with dark matter. It's a galaxy where dark matter is the galaxy, with stars as little more than accidental ornaments. What makes Dragonfly 44 so baffling isn't just its darkness, but its defiance of galactic norms. Most galaxies this massive, with a stellar disk spanning 60,000 light-years, boast bustling spiral arms or dense elliptical cores. Dragonfly 44, by contrast, floats as an ultra-diffuse galaxy, its stars so thinly scattered that you could fly a spaceship through it for centuries without nearing a single sun. Yet strangely, it's teeming with globular clusters. 94 of these ancient star swarms orbit its core, nearly twice as many as the Milky Way hosts. These clusters shouldn't exist in such abundance around a galaxy so faint. Normally, globular cluster counts correlate tightly with galactic mass, but here they outshine their pale parent galaxy like fireflies around a dying ember. The answer lies in the dark matter scaffolding holding this ghostly structure together. Measurements of star velocities reveal Dragonfly 44's dark matter halo weighs a mind-bending 2 trillion times more than our Sun, making it as massive as the Milky Way despite having almost no visible matter to show for it. This imbalance has theorists scrambling. Current galaxy formation models suggest dark matter's gravitational pull should have attracted enough gas to form far more stars than we see. So why didn't it? One provocative idea proposes Dragonfly 44 is a failed galaxy, a place where dark matter's grip was so overpowering that it strangled star formation before it could truly begin, leaving behind a cosmic fossil where gas never ignited into starlight. There's another possibility, even more radical. Dragonfly 44 might be the survivor of a cosmic near-death experience. Some simulations suggest galaxies like this could be the stripped remnants of once normal galaxies, their stars and gas ripped away by violent encounters, leaving only their dark matter skeletons and a handful of resilient globular clusters behind. Supporting this, the globular clusters orbiting Dragonfly 44 are unusually metal-poor, a sign they formed in the early universe before later generations of stars could seed them with heavy elements. They might be all that's left of a galaxy that was otherwise shredded by gravitational tides, a shipwreck's floating debris marking where a greater structure once sank. Yet for all its oddities, Dragonfly 44 isn't alone. Surveys have uncovered dozens of similar ultra-diffuse galaxies in the Coma cluster alone, hinting that these shadowy giants might be far more common than we ever imagined. That realization has sent shockwaves through astrophysics. If entire populations of galaxies exist with almost no stars but staggering dark matter reserves, our models of how galaxies assemble and how dark matter behaves might need a fundamental rewrite. Are these dark galaxies the rule rather than the exception? Could the universe be teeming with invisible giants we've only just begun to detect? Every new observation peels back another layer of Dragonfly 44's mystery. With telescopes like JWST and the upcoming Rubin Observatory training their sights on these cosmic phantoms, we may soon learn whether they're galactic oddballs or hidden keystones in the universe's structure. Until then, Dragonfly 44 stands as a haunting reminder that the cosmos still guards its darkest secrets not in the voids between galaxies, but in the galaxies themselves where light barely dares to tread. Rising from Andromeda's core like a pair of ghostly searchlights, newly discovered gamma-ray bubbles mirror our own Milky Way's Fermi bubbles with uncanny precision, but with twists that could rewrite what we know about galactic eruptions. Stretching 50,000 light-years above and below Andromeda's disk, these colossal structures glow with the same high-energy radiation as their Milky Way counterparts, suggesting a shared cosmic blueprint for how giant galaxies unleash pent-up fury from their cores. Yet the differences are just as telling. Andromeda's bubbles are slightly dimmer, more asymmetric, and curiously offset from the galaxy's exact center. Clues pointing to a history of black hole outbursts that might be messier or perhaps more frequent than our own galaxy's past explosions. What makes these bubbles so fascinating isn't just their size, it's their timing. Our Milky Way's Fermi bubbles likely formed in a single cataclysmic event between 2.5 to 4 million years ago, when Sagittarius, a star, woke from its slumber to devour a passing gas cloud or star. Andromeda's bubbles, by contrast, show layered signatures in their gamma-ray emissions, hinting at multiple eruptions spread over tens of millions of years. It's the difference between a single gunshot and sporadic volleys, a pattern that suggests Andromeda's central black hole might be a more restless sleeper, stirring to activity in fits and starts rather than one grand awakening. The implications ripple far beyond these two galaxies. If both the Milky Way and Andromeda, the two largest galaxies in our local group, bear these gamma-ray scars, could such outbursts be universal? Observations of distant galaxies add weight to the idea. Around 30% of massive spiral galaxies show X-ray or radio evidence of past central explosions, often accompanied by faint, bubble-like lobes in their halos. Some theorists propose a cyclical pattern. Black holes binge on infalling gas, erupt in gamma-ray fury, then enter a quiescent phase until enough material accumulates to trigger the next outburst. This boom and bust cycle could be critical to regulating galaxy growth, preventing gas from cooling too quickly and forming stars uncontrollably, a cosmic thermostat coded in gamma rays. Yet mysteries loom. Why do some galaxies, like the nearby spiral M81, lack obvious bubble structures despite having active black holes? The answer might lie in environment. Dense galaxy clusters funnel more gas toward central black holes, making eruptions more violent and visible. Isolated galaxies like M81 might experience softer, more continuous outflows that don't inflate distinct bubbles. Alternatively, the bubbles could fade faster in certain conditions, leaving only subtle traces in older galaxies. The most tantalizing question is whether we're seeing gravitational echoes of the local group's future. In 4 billion years, when the Milky Way and Andromeda collide, their supermassive black holes will spiral toward each other, potentially triggering outbursts that dwarf anything in their histories. Simulations show such mergers could produce gamma-ray bubbles spanning hundreds of thousands of light-years, temporary monuments to the chaos of galactic rebirth. Until then, studying these structures in both galaxies offers a rare chance to compare cosmic fingerprints, revealing how two similar yet distinct titans manage their explosive tempers. One thing's certain, black holes don't just shape their galaxies, they shout their presence across the void, painting the cosmos with light only the most powerful telescopes can see. These 25 galactic enigmas aren't just isolated oddities, they're pieces of a cosmic puzzle, so vast it reshapes how we see the universe itself. From the Hercules-Corona Borealis Great Wall's impossible scale to the eerie silence of the Boots Void, each structure whispers a tantalizing secret. The cosmos refuses to play by the rules we've written. Dark matter's invisible grip, glimpsed in the Bullet Cluster and Dragonfly 44, seems to orchestrate galaxies like a hidden conductor, while phenomena like the dark flow hint at forces beyond our observable horizon, perhaps even other universes tugging at the fabric of our own. And let's not forget the violent beauty of colliding galaxies, where destruction births new stars, planets, and the very elements that make life possible. What ties these mysteries together is their defiance. They challenge the cosmological principle's assumption of uniformity, upend our models of galactic evolution, and even question whether gravity works the same way on all scales. The giant arc's perfect curve shouldn't exist, yet it does. The cold spot in the CMB might be a bruise from a multiverse collision or something even stranger. Every time we think we've mapped the heavens, the universe reveals another layer of complexity, laughing at our attempts to fit it into neat equations. This isn't just about solving puzzles, it's about rewriting the story of everything. Could dark matter be more dynamic than we thought, shaping itself into filaments and halos we've barely begun to detect? Are we, as the KBC Void suggests, floating in a cosmic anomaly that skews our entire perspective? And what other structures hidden by dust, distance, or dimensions are waiting to be found? The telescopes of tomorrow, like the Vera Rubin Observatory and the James Webb Space Telescope, promise to peel back more layers, but one thing's certain: the universe will keep surprising us. So keep looking up. Every strange glow, every unexplained motion, every silent void is an invitation to wonder. The cosmos is far wilder, more inventive, and more mysterious than we've dared to imagine, and the adventure is just beginning. If you're as captivated by these cosmic riddles as we are, make sure to subscribe and hit that notification bell. The universe isn't done revealing its secrets, and neither are we. Until next time, stay curious and remember, the greatest discoveries often start with a single, impossible question.